anytime because he wouldn't have been there if you came by at 10 o'clock or 11, 10 o'clock or 12 o'clock. Those both times I called and he wasn't there. So, but they do public showings, but I think they have to be arranged. It's not like a continuous show. He sets up something for the groups coming in. And he may have high school groups in the summer. He may be just up to his head in the summertime. So I don't know. See, last summer the Physical Science 112 class didn't make, so I don't know what happened then. Summer before last, I don't remember if it made or not, and if we were able to schedule a visit or not. Sometimes summers, because people take vacation and stuff, sometimes hard to work in. Okay, so I won't know until maybe at earliest after 3:30 whether we'll be able to go Tuesday or Thursday of next week or some later week. So I just don't know that. And if I find out we can go on Tuesday, I'll put it on Blackboard under announcements, and you'll get an email too. So watch that up to before class. Now here's what I told them. I couldn't remember if any of y'all had classes right before this one. Do you? Yeah, I thought so. So I told them the earliest we could be there would be 12:45 because I figured it takes us about 45 minutes to get there. Okay? And then do any of you have classes right after this one? Okay. So I told him I thought he could go up until 3:30, or I said pick an hour or two, whatever you want to, length you want to do, in that window from 12:45 until 3:30, and we'll try to be there. And I tried to tell him I was running out of messages in. Rather have it on the front end or the back end if possible, but if not, anywhere in between would be fine. Is that okay? I was just going by. I never noticed any of you say, look, I got another class, I got to go. It seemed like y'all were always fairly relaxed at the end, and that's sitting late enough in the day. I was thinking you probably didn't have any classes. Now, where we left off last time was doing the lab for phases of the moon. Okay, and we almost finished it, but not quite. So let's pick up there. Unless there's other questions, I'll be glad to try to field those questions before we do this. Any questions? Anything we've done so far? All right, before we start on this, then let's just go over. As my memory is, we just got the last page on this to go. Okay, so we'll do the last page. It won't take us very long. Then we'll get into chapter 17. And then once we're through with chapter 7, that will go up until 3. Okay, I don't think we'll finish 17 in that time. We might, but if we do, that's fine. But then at 3 o'clock, we'll stop everything and have the test on chapter 16. Okay, sounds good? Okay, especially the test part. Okay. Now, if we do finish 17, I've got the lab made up. We can either start it today or get started on 18 and do the lab on next Tuesday or whatever. So we'll decide that when we get closer to that. All right, last page on the lab, the moon lab. Okay. Now I think I'll get my globe out here. I've got the sun in place. Now, page 384 of the last page of the lab. By the way, in case you didn't hear it, I did get my first paper in for this class. Way to go. So y'all keep them coming, okay? Way to go.
I'm trying to make us look bad.
Huh? Well, now, wait a minute. I don't think she can help that. I didn't say that. Okay. Okay. I'll use this if I need to. At what time of day do you expect the full moon to rise? Make a guess. Huh? around noon. Second.
Dust. As soon as
Dust.
it gets night.
Okay. Believe you're closer to it then, and here's why. Where is the moon when it's a full moon? It has to be facing you, right? Facing the sun. Here's the sun, okay? Facing the sun, okay? Now this would be, for us, for at nighttime, when we can see that, that's going to be midnight, okay? So when would it rise? Well, here's the key, okay? Here's the key. The moon's here, and you're there, and we're in between. It's exactly opposite. So therefore, when the sun's rising, the moon's setting, and when the sun's setting, the moon's rising. So you're right around dusk, or you could say around 6 p.m. Either one of those would be a legitimate answer. Okay? Now, when would you expect the new moon, or a very thin crescent moon to rise?
Early morning.
Early morning, because it's on the same side as you. That's why you don't. It's a new moon. You don't see any of it lit, so therefore it rises with the sun.
I recorded it yesterday.
You what?
I recorded it yesterday.
Oh, you did? Okay.
It's 5 o'clock.
Oh, wow, super. And that was a new moon?
Yeah.
Oh, super. Okay. Which means, okay, let me think about this. And you can see it this morning. Well, you can't see it very well. Okay. Just to show.
Off of new moon.
Got
Just straight on.
Okay. And the morning before, could you have seen it, or do you know?
It was there. It was kind
Oh, it was?
Yeah.
Earlier or later?
It was about the same time, about 5. Just about
Okay.
the time I get up.
Okay. But it was decreasing or increasing?
Couldn't tell that.
Huh?
I couldn't tell that.
Yeah,
I
that
really
was-
didn't notice because I didn't get the sign.
Okay. What I was trying to think is the moon, so it's moving earlier or later right now.
It's just coming off the moon.
Well, that would have been 2 weeks ago.
Yeah.
So it's going to it. So I would say early morning. I think it's more like late at night, right around sunset. I believe this is right. You'll start seeing it. So this is not a bad time. Have you even tried to get out there and do your initial thing? I know you wouldn't be able to see the moon. Has it been too wet? Okay. Try to get something done in the next day or two because, well, depending on what doctor. If you're an early morning person, you're going to watch it. It may have just ended for you. It's going to be 2 more weeks. If, however, it's moving the other way, and that's what I can't remember now, perfect attendance again. This class has to be the very best attending class. First day, I had 3 out of 4 of you here. The next day, all 4 of you were here, and I don't think anyone's missed a day since. Okay? Way to go, team. I've not had a class do that well ever, I don't think. So y'all are exceptional, of course. Okay. Of course, it's a small class, but still, sometimes, like this morning's class was even smaller, and I was afraid nobody was supposed to show up, but one person did. Okay. So here's what we were just talking about where and when the moon is, and it was just the new moon change, right? Was setting, yeah. So early morning, and I just can't remember. I'm pretty sure in the around dusk you'll start seeing a little crescent, and then it won't be up long, just a little bit. But every night will be a little bit longer. So I'm thinking if you're a morning person, you might have to wait 2 weeks before you start seeing it. Okay, but just keep looking. Okay. If you're an evening person, stand by, depending on what time of night you're going to make your observation. It's going to be coming up soon, I think. Okay. So we just did, on page 384 on the lab, the last page, we just did 5A and 5B. 5C, when would you expect the first quarter moon to rise? Now, first quarter moon, remember, this is the new moon. first quarter moon would be over here, right? Because it goes counterclockwise. Yeah. Okay. Counterclockwise. The first quarter moon would be right over here. Okay. When would that rise? Okay, the Earth spins this way, and here's Birmingham, Alabama, and the moon's over here. You would first begin to see it. Second, late morning, right around noon. Now look, the sun's right overhead now, and you just are seeing that first quarter. So that would be right around noonish. Could be on the morning side or afternoon side, but right around noon. Does that make sense? Okay? Third quarter moon to rise. They name these things so many different things. Most of the time they call it last quarter, but they only call it third quarter. Okay, last quarter moon to rise. Where's the last quarter moon? Over here, right? Okay? And when would that rise? Earth spinning this way. I've got Birmingham right in front of me here. It's right when you just begin to see it. What time of day is this? Midnight. Midnight-ish. Okay? So that's number D. How about that first quarter moon to set? Okay? Remember here it's our first quarter moon, right? And when is it setting? Oh, I think it's because it's spinning this way. Birmingham is set now. What time would it be right around the time it sets? With Birmingham. Midnight again. First quarter moon would set right around midnight. And the new moon or very thin crescent moon to set. Where is a new moon or a crescent moon? On the side toward the sun. That's why you don't see anything. All the side that's lit is toward the sun, and we only see the dark side, if you can see it. And when would that be? Setting. Right there with the sun. When the sun sets, it would be set. So sunset, or 6 p.m.
Which one was that?
Huh? That's yeah. New moon or very thin crescent moon to set. Does that make sense? I mean, the new moon is right with the sun. That's why it's a new moon. So if the sun's rising, the new moon's rising. If the sun's setting, the new moon's setting. So that new moon is only visible during the daytime. That's why you can't see it very well. It's not lit, but every now and then you might see an outline of it, just the back side of it. That's why you see it. All right, that finishes the lab. Any questions on the lab? Oh, I thought that was a siren at first, but that is a weather thing. Do y'all have anything? Huh? Now, for weather emergency, we don't go out. We stay in. I don't think it's tornadic, so I don't think we'll have to go down. I'm guessing it's flash flood. I don't know why I would guess that. Okay, it hasn't rained every day for 40 days. No, I didn't say that. Okay. What's that?
Warning? That means something is on the ground.
Thunderstorm cable produced a tornado located over Fairfield, moving northeast.
Okay. So Fairfield is to the east of us and north of us already, so it's moving that way. I think we're okay. I hope your phones are right. Which kind of reminds me, and I said this before you came in, Brian, but it's just been a crazy morning, and probably be a crazy day all day, maybe not. But one of the things that took my 1 hour that I was going to be grading papers, didn't get that one graded, was I had a call from one of my adjunct instructors who thought he left his book on top of the vending machine because he got something right before he went out. And when he went out, the door locked behind him, and he couldn't. And that's when he realized he didn't have his book. He thought he left it there, but he couldn't get back in the building to see it. So, and he had his ride was waiting on him. So he called to see if I could check out and see if it was there. Well, I spent most of the next probably half hour or so scouring the building and checking with police and the front desk and the bookstore and everyone I could think of to see if anyone had seen his book. Then I had to call him back. Well, all that was going on. He had called the campus police number that he had, which was Officer Tate, Lieutenant Tate, and he had called him last night, no, I think it was this morning, to see if anyone had turned in his book. I didn't know he had called. I was in class this morning. That's why it was after 10 before he called me. Okay? And when I went down to check with Officer Tate, I didn't know he had already called him. He said, no, math book, no. I said, how'd you know about it? Because when he first said it, I thought, oh, they found it. He said, no, he called. And he said, and please tell all your adjunct instructors not to call my office because I could be in Montgomery. I could be on the other campus. I could be anywhere. And the instructor complained, said, you weren't there to answer. He said, no, I was out doing my job, you know. So he said, please give all your adjuncts the best number to call, and this is the number that goes to the radio that the on-duty person has, so there's always someone with that radio. Whenever there's a person here, somebody has that radio. And I said, good, give me that number, and I'll give my students as well, because I've told them at the beginning of every term, good idea to have the campus police number in your phone, but I never knew what number to give them. He gave it to me today. So if you want it, to have it, here it is. 426-3654. 426-3654. I'm going to keep it in my grade book. I'm going to try to remember to tell all my classes that's the police number. It's not necessarily an emergency number, but it can be used for an emergency. But somebody, if there's a police on duty, one of them's going to have that radio, and they will be able to hear if you call in and respond to you. All right. That done. Any questions? Chapter 16, the lab on 16, and just a little bit of a refresher. Brian, we're going to start 17 now, and we will go until 3 o'clock. At 3 o'clock, if we have finished 17, we'll decide then whether we start the lab or go on to start 18. If we don't finish 17, we'll pick that up again on Tuesday. Oh, and here's the other thing. I should tell you this too, because I said it to the others. I tried calling at least twice today to get in touch with Mr. Weigel at the planetarium. Both times I got his voicemail. He didn't indicate that he was away or out for the summer or out for a week or so. He just said, sorry, I'm not at my desk. Leave a message. So he may have forgotten to change his phone. For instance, when I was in New Orleans for 2 days, I didn't change the message on my phone, so he may not have either. I don't know. So I'm going to try again after the class is over at 3:30 to see if I can get in touch with him. If he wants us to come next Tuesday, I'll put an announcement on Blackboard, and be sure to check that before you come to class on Tuesday, okay? Or be prepared, if you don't check it, be prepared to go if he says go, because we'll meet here. If he says come Tuesday, we will meet in this classroom and head out from here, okay? So if you're going to be late and you come up and we're not here, I'll probably have a note on the board. We're at the planetarium, come on over, okay? Now, what I don't know if he does shows for as few as 4 people, 5 people. So I told him it was a very small class, so I don't know. I think he'll do it, but I said you can combine us with another group if you want to do that, because we don't take many seats, okay? And then again, I did tell y'all that you could bring other people, just so we'll have a bigger crowd. Are any of you planning to bring anyone? Family member? I've had people bring their kids before. I've had them bring their spouses before. I think I've even had one bring a parent before or something. So you can bring a relative, a friend, a brother, sister, cousin, if you want to. You don't have to, but But I told him that I had opened it up because I thought he wouldn't mind having a bigger crowd. But any of you have any guesses?
I'll probably have at least one.
You what?
I'll probably have at least one.
At least one. Fantastic. Anyone else planning to bring anybody? Usually they don't, but you're welcome to do it. And he's always welcome to support you. Okay. If no more questions on 16, let's get started on 17. Now, the general breakdown again for the course: astronomy, the first 3 chapters; general classified earth science, the next 4 chapters, 17, 18, 19, and 20. Then weather and climate, which I think is 23, and Earth's waters, which is oceanography or Earth's waters, that would be 24. Have I got the numbers right? It's, 23 and 24. Okay? So this begins a 4-chapter group on earth science. This first part is pretty close to getting what you would call geology. Okay? Though all of it could be called geology. Earth science is a little more general. Encompassing. Rocks and minerals. Now, you see something like this in your picture. It's not the same, but it looks like the same mineral. I believe this is rhodochrosite, which is a naturally occurring form of manganese carbonate. Very beautiful crystal. Okay? Now this one looks a little more angular than the one that I'm looking at in the book, but I believe that's the same thing. But none of you have the old books to see. But anyway, we're going to be talking about stuff like that. They won't all be that pretty though, okay? Here's the core concept. That's near the top half of the chapter page. Earth is a dynamic body. What does that mean? Dynamic? As opposed to static. Static is stationary still, nothing changes. A lot like what the moon is right now. It's pretty much stable. And the earth is stable, but it's always changing. Maybe slowly, but it's always changing. So earth is a dynamic body that cycles rocks and minerals through ongoing changes. Nothing stays the same. Okay? It's pretty similar for a while, but nothing ever stays the same. Okay? Just like us. No matter what, we're always aging, right? Unfortunately. Okay? Some of us more than others, but never mind that. This, however, is one of the oldest rocks, I think, that has been found. They have dated this somehow, and we'll be seeing a picture of this later. I don't think this is in your text at this point. I think it'll be in the later part of the text. Again, this is the first time I've taught from the new edition, but we will be talking about that rock a little later. What are some things you notice about it? What's the first thing that strikes you about it? The what? Okay, yeah, the colors, the striping, the layering. Okay? Now, anytime you see a rock that has layers like that, you know at one time it was a sedimentary rock. Those were the only ones that formed layers like that. Okay? But what settles like that? Nothing. There it is again. Okay? What this means is after it layered, and it layered horizontally, then it went through an incredible amount of pressure and changes to warp and bend and twist the layers like this. So this is a rock that has been around a while, okay? First, it was a layered rock, sedimentary rock. Later, it was changed and malformed by more pressures. Probably a lot of temperature as well. We'll talk about that later. Okay. Let's look at 17.1, which is Earth's solid materials. Is that anything new, or is it the same one? Just, is that the same thing? It must be a tornado somewhere, but hopefully going the other way. Okay. Earth's solid materials form a non-uniform distribution of matter. Is that okay? What does it say? Same thing, Fairfield going northeast?
Yeah, they're extending it on north.
Okay, yeah, but going away from us. Good. I mean, I'm sorry for those people. I'm glad it's not coming toward us. Okay, what does it mean by a non-uniform distribution of matter? What does that mean to you when you read words like that? Okay, yeah, okay. You have things that are concentrated in one place and not another. That means non-uniform distribution. You can't just, I've done sampling before, both usually soil sampling, but also tube-type sampling. And you can't figure you can just take a core somewhere and go as deep or as far as something as you want, bring it up, and it's going to be the same as one you get over here. In fact, from here to there, you make it as a non-uniform distribution. If it's uniform distribution, all your cores will be the same. They're not. Okay? What's more, as you go into the earth, things change really, really big. Not just on the surface, but into the earth. Now, here's some of the changes. Our core is molten. What do we mean by molten? Okay, melted, molten, okay, liquefied, yes, exactly. A molten core, and the core contains the most of the heavy elements. Because guess what? Heavy things settle out, lighter things go to the surface, right? And that's what we find. It contains most of the heavy elements. The primary ones in the molten core are iron and nickel. Now, iron and nickel are not the heaviest metals out there, but they're some of the heavier, commonly occurring metals out there. Here is iron right there in the periodic table. That's just on the fourth row and just about the middle column. And you got many more rows below that than you had above it. Okay? It's number 26 out of 100 some odd. It's only about a fourth of the way down there, okay? But it's one of the heavier, okay? And here's why we say that. If you remember what we talked about with star formation, fusion that goes on in stars, that's where most of the matter is, by the way, in stars. Fusion is hydrogen to helium. Those are the two lightest materials there. Later, on the bigger stars, you get helium to carbon, and then some of the really big ones, you'll get carbon to higher things, up to iron, and after iron, they don't spontaneously go to iron. They don't. That's not the normal process. Now, when you have the supernovas, when you have enormous explosions, then yeah, some of those heavier elements may fuse iron and beyond. And that's where we get our uraniums and our radiums and those other really heavy plutonium and these other things that are very, very heavy is when that happens.
So, Don, you ordered a tornado warning supposed to go downstairs at
We are.
1 o'clock. There's a siren that just went off call.
Okay.
You able to send me something and say go to a shelter place till 1?
Till 1.
Yeah, about the next 15 minutes.
Okay. All right. Thanks. Well, I guess we do have to go down. We've been following it too, and we'll try to move on. Now, Amber, do you have to leave early, you think, or do you know? Oh, you don't? Okay. Okay. I thought you said the trip.
She walked with me by two, but I told her I could have a text.
Okay. All right, I'm waiting for the projector to light up enough for you to see. There it coming. All right. So the molten core of the Earth is the heavier elements, iron, nickel predominant, but then you have other heavy ones down there as well. We live on a very thin surface crust. Now, when I say very thin, it only goes a few miles deep. Now, that sounds pretty deep to me, but compared to the entire Earth, that's a thin little crust of it. These are mostly the lighter elements on the surface. In fact, look at your periodic table and the stuff, anything above iron. Okay? Now, get this. 8 elements of the 100 and some odd elements we have, 8 elements make up 98.6% of the crust. The vast majority of the crust. Almost all of it. Okay? We're going to see the slide in just a minute. The rocks and the minerals make up the solid crust materials. Then we have liquids, and then we have gases on the atmosphere and stuff. But rocks and minerals make up. And that's what this chapter is about, rocks and minerals. Okay? Here is the diagram that illustrates what we're talking about. This is in the Earth's crust. Almost half of the crust is made up of oxygen. Of course, what is oxygen? When you think oxygen, what do you think? Gas that you breathe. That's not what they're talking about. We're talking about the solid material in the Earth's crust. How can oxygen be a solid material? Okay? I think you know the answer to part of that right now. Has anyone ever heard of, well, let's just go back. That picture on the previous page, rhodochrosite, is made up of manganese carbonate. Manganese carbonate. Manganese is Mn, and if you got your periodic table in front of you, it's number 25, the one just this side of, on the lower side of iron. Carbonate, the carbon is number 6, okay? The ATE, carbonate. Does anyone know what that stands for? Anytime you see an 8 or an ite in a mineral name, ATE or ITE, it means oxygens. Carbonate, CO3. So you have 1 manganese, 1 carbon, and 3 oxygens. So most of that mineral, that red rock that you see, pretty red rock there on the thing, that's mostly oxygen. Huh. Who would have thought it, okay? Because oxygen makes up an awful lot of, and we'll see this a little bit later. So yes, this is solid forms of oxygen compounds, oxygens in compounds. If you think about it, what's in your glass right there? No, in your bottle. What is in that? Okay, what is water? Huh? The most of it is oxygen. It's H2O, but if you look at the periodic table, H is 1 and 1, that's 2, H2. O is 16. So of every 18 grams, ounces, whatever you want to call, of water in there, 16 of those are oxygen. And yet it doesn't look like oxygen. We don't use it as oxygen. It's a compound, water. Not a gas, a liquid. And most of that mass is oxygen. Strange, huh? But chemical compounds, and we'll do this in another course, chemical compounds combine things that are very unlikely to make things that are very different from what they were. So that's why oxygen, sure enough, in compound form, makes up a lot of solids. Next sector oxygen is silicon. Okay? Oxygen, by the way, is in the second row on your periodic table. It's number 8. Okay? Silicon, more than a quarter is silicon. Silicon is just below carbon, and it's number 14, so it's almost 25% of the Earth's surface. Now, where do we find most of our silicon? Say again? Okay, computer desk, that's where we use silicon, Silicon Valley, right? Okay, but where we find it out in the on the planet, most sand crystals that you'll ever see, most, not all, most sand crystals are silicon dioxide. 2 oxygens, 1 silicon, or actually more like 3 or 4 oxygens and 1 silicon. Okay, so that's where it is. It's in all your rocks and minerals. Most of them have silicon. Okay, almost a quarter of the crust is made out of that. So when you combine oxygen and silicon, more than 3/4 of the crust, almost 3/4 of the crust, is made out of those 2, just those 2 elements alone. After that is aluminum. Now you don't find very much pure aluminum. We're not talking about aluminum cans as trash. We're talking about ores, aluminum ores. Well, how about that clay? Isn't Alabama pretty famous for its clay? I know Georgia is. Clays are all over the place. Most of those clays, at least in Georgia, I think it's true in Alabama too, are what they call 1-to-1 clays. One layer is silica oxides, and the next layer is aluminum oxides. The silica oxides are 1 silica for 4 oxygens. The aluminum oxides are 1 oxygen for maybe 6. I don't think it's that many. 3, maybe. Something like that. So anyway, that's where a lot of aluminum is. It's not as aluminum ore, or pure aluminum, nowhere close. Most of the rocks out there have aluminum oxides as well as silicon oxides. Now iron, which is very predominant further deeper down, most of the core is iron, even on the surface you have quite a bit, 5%. I bet you in Red Mountain it's more than 5%, okay? Places where iron ore comes to the surface. That would be, so iron is number 4. Calcium, number 5, at 3.6%. Doesn't sound like a lot, but you know what underlies most of the state of Alabama? Over in Georgia, the bedrock is mostly granite. Okay? In Alabama, it's mostly limestone. And you know that. You drive down the road, you see limestone outcroppings on either side, you know, where they made the road cuts. Lots of limestone here. In fact, a lot of companies, I think Drummond probably does a lot of limestone mining and grinding and shipping it out. Okay? What's the town a little bit north of here called? Starts with a D. Small town. Dolomite. That's a type of limestone. I don't know if they have it there, but I bet you they do. So calcium is in limestone. Calcium carbonate. Again, calcium, carbon, and 3 oxygens. Okay, so it's mostly oxygen, but also has a fair amount of calcium. Sodium is next. Now, pure sodium, you don't find much of that, but a lot of sodium is in sodium chloride is a salt, sodium carbonate, sodium hydroxide, sodium, all sorts of things. Sodium phosphate, sodium nitrate. Sodium is pretty prevalent, 2.8%. And then potassium, 2.6%. Now those percentages are sort of funny and strange because if you were to test your blood, you're probably not going to be too far off from that percentage of sodium and potassium. Potassium is one of those elements that are necessary for plants to live. There's several of them that are. But the big 3 fertilizer elements, does anyone know what they are? When you see a bag of fertilizer, it usually has something like 6, 12, 12, or 5, 10, 15, or anything like that. Those 3 numbers are the percentages of the three most important elements to plants. Nitrogen's number one. I always get the other two crossed up. I believe it's then potassium, then phosphorus, or phosphorus and potassium. I don't remember which. Potassium's one of those big ones. And I want to say, I'm scared to say it because I'm afraid I might get it wrong. It seems like to me, what's one of the most important cells that are in your blood? The ones that have carry oxygen to and from, to all the muscles and everything. Say again?
Is it the red blood cell?
The red blood cells. You know what makes them red?
Oxygen.
No, it's iron. Hemoglobin. Okay? Hemoglobin is the part of the red blood cells that carries the iron, that has iron in it. And the reason the iron is there, it's in the middle of a claw-like molecule. Now I'm saying it wrong. Okay. Take that back. But that's still true. Iron is there. And it has oxygens and carbons and other things around it. It's in a big claw like that. And it goes around and the iron changes to ferric oxide when it's exposed to the oxygen in your lungs, and it becomes red blood, arterial blood. It then goes down to your muscles, to your eyes, to your brain, to everything that's operating, your stomach if you're digesting today's lunch or whatever, you know. The oxygen, it picks up the oxygen, carry it there, and then your body extracts the oxygen from the hemoglobin and makes it ferrous oxide, which is a lower order oxide. Okay? And that is a dark grayish bluish color. And that's why your veins are blue. Going back. Well, what I was going to say, I was thinking it was potassium. It's not. It's magnesium. So I'm sorry, I had that wrong. But potassium is essential for plants. It's essential for humans. Here's what I was going to say about humans. The sodium and potassium balance is so critical because that potential difference between a sodium ion and potassium ion, that's what sends the electrical signals that make you able to hear and process that hearing, see, process that sight, sends the signal to your blood, the heart, pump, 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 pump. If it wasn't for that the proper balance between sodium and potassium, you're dead, okay? And sure, we get plenty of sodium. There's sodium in everything. What are you eating right now? What is that, by the way?
Chicken.
Chicken. Now, I bet you it's salted chicken, isn't it? Of course. Everything has salt in it, okay? But not everything has potassium in it. And especially if older people, my mother, for instance, she had some condition that made her legs swell really badly during the day. At night when she was sleeping, the swelling went down, and the day when she was up, it came back again. So they started giving her a diuretic to help pull that liquid out of her veins because she just wasn't efficient in pumping, getting it pumped out. You know, she had to be prompt. She didn't like being prompt. She liked doing things. So they gave her a diuretic, and the diuretic made her evacuate, you know, more and more frequently. And what they didn't realize, she was losing some potassium, had plenty of sodium, and she just a few times just got like she was losing her mind. And no one knew what was happening. She got so weak and disoriented and everything, they rushed her to the emergency room, and they found out it was low potassium because the diuretic was taking too much out of her system. So from then on, she had to take these big old fat potassium pills, and she never had that problem as long as she was on her pills. A couple times she ran out, and she went right back to that condition again. If we don't have that proper balance in sodium and potassium, we're dead. In fact, pretty sad expression of it. I can't remember the compound. Potassium something or another. Pretty common compound. They used to use for lethal injection. Because as soon as you got that balance messed up, your nervous system shut down. Stop sending signals to the heart, it quit beating, you're dead. And so it is something that has been used as for lethal injection. Okay. Magnesium, that's the one I was trying to think of. That's number 8. 1, 2, 3, 4, 5, 6, 7, 8. Magnesium, that's also in the soil to lower extent than some of these others. These are all lightweight elements. Top part of the periodic table. Most of them in the first couple of rows. Iron's in the 4th row. Silicon's in the 3rd row. I think just about, and potassium's in the 3rd row. No, potassium's in the 3rd row. Magnesium's in the 3rd row. The rest of them are in the 2nd row. Okay? So, all of them way up there. Okay? Iron's the heaviest one of these, any of them. Now, magnesium, that's what I was starting to say. Whereas our hemoglobin, that carries the oxygen to all parts of the body and then transports the carbon dioxide back, that is that claw-looking material that has carbons and probably some nitrogens and oxygens and hydrogens around it, but with that central molecule of iron. Now, what's special about those green leaves out there? What's in them to make them green? Okay? Sure, oxygen's everywhere. But what is the thing that... Chlorophyll. Chlorophyll molecule, you might say, looks just like, or almost identical to a hemoglobin molecule, except rather than iron in the middle, the claw is around magnesium. So every green plant out there. Well, do we care? Does chlorophyll do anything for us? We don't have it. What does chlorophyll do for the plants? And for the planet, by the way.
It helps emit
Helps do what?
something.
Okay. It's almost the reverse of what happens in our blood. The plants take in carbon dioxide and it pulls out the carbon and releases oxygen. Okay? And if it weren't for that, we're dead. Because without green plants, we don't have enough oxygen to breathe. They're constantly producing oxygen. And we are constantly inhaling oxygen. And again, take a look in that chapter 15, that table for the atmospheres. And the terrestrial, of course, Mercury hardly has any. Venus has largely carbon dioxide, right? It has no green plants. Go to Mars, largely carbon dioxide. It has no green plants. If we didn't have green plants, our atmosphere would have a lot more carbon dioxide and other things in it. But what green plants do is keep the carbon dioxide level low and keep the oxygen level up there. Okay? And if it weren't for green plants, life on this planet is over. Okay? Now, with that said, where is the biggest abundance of green plants? Second? Rainforest, you're absolutely right. And most of those are the tropical rainforests, right? And guess what countries are doing to tropical rainforests? Cutting them down. Now, for some, they're harvesting some of the wood and using the wood. That may be all right. But the vast majority of the wood is bulldozed into big piles and set on fire. So what are we doing with all that cellulose? We're burning it and making carbon dioxide going into the atmosphere, and that's using up the oxygen to burn it. And what was our biggest producer of oxygen is now becoming, because of man, becoming a huge producer of carbon dioxide.
Now, is that still as significant as it was years ago?
I don't know. I had thought maybe not until I saw something fairly recently, within the last year or two, that in Indonesia and other places like that, they are destroying tropical rainforests so that they can plant palm oil trees. Because if you look at most of the ingredients in most of the food these days, they're not made with animal fats anymore. They're not made with, I mean, some are made with soybean oil and, corn oil and stuff like that. But the vast majority of the fat that you'll find in the products you eat and the products you find in the store is palm kernel oil. Because they can produce that so fast. Tropical rainforest, they grow like weeds, produce a lot, much faster than soybeans and corn and other things. I mean, it produces it. And they have destroyed great tracts of land that were tropical rainforest and just planted palm trees that produce the palm kernel oil. And look at the ingredients. Do it. Pick up any package that you see in the house, start reading the ingredients. When you see the oils, the vast majority of the time, palm oil will be near number one, if it may not be the only one in there. Because it's cheap, and they learn how to do it, mass produce, stuff like this, they can just really put it out there. Much cheaper than we can do soybean oil and corn oil. So you can do it year round in the tropics, you don't have a season. So until I heard that, I would have said, yeah, they probably have cut back on that. But then I've heard in other areas, because I was thinking mostly Brazil. Brazil was cutting down the tropical rainforest to plant soybeans and corn and things like this to harvest, because Brazil was trying to get away from imported oil because they don't have any oil, but they could produce a lot of soybeans. So they were trying to become energy independent through that. So they were cutting down tropical rainforests to do that. Well, soybeans put out oxygen too, not nearly like a huge canopy of tropical forest would. And then, so I think Brazil has cut back doing that, but I think other countries have started doing palm oil and things like this. So I'm not convinced that we have the system. Some people have, other people are just, hey, let me get in on this game. It's profitable, unfortunately. Okay. So magnesium, very vital. We need magnesium too, but plants need it like crazy. Okay? We'll talk more about that later. Now, let's go to the whole Earth, which includes the core. We'll talk about these pieces later, the mantle and the crust. And there's a lot more core and mantle than there is crust. Then when you go to number one, suddenly the iron, like we said before, that's the biggest. So in the molten core, that's by far the biggest. But in the whole Earth, it's the biggest. A full third of the solid material in the planet is iron. Almost a third is oxygen. Okay, same as here. That's in solid form because it's in compound form. Silicon has dropped down to 15, about half what the percentage it was there. And magnesium has certainly come from being number 8 to being number 4. And then comes nickel. And it seems like to me, why do they say iron and nickel when nickel is pretty small, but in the inner core, nickel percentage is much higher and iron is higher too. And then calcium, which was about where it was before, but a lower percentage. Aluminum has dropped down because it's really light, so it's down there. Sodium is next. So 1, 2, 3, 4, 5, 6, 7, 8. Sodium is 0.2 in the top 8 there. Okay? And then you have the others. So,
Nitrogen.
what's that?
Okay. Nitrogen.
Okay, nitrogen is in the atmosphere, mostly as gas.
Okay.
Okay, about 80% of the air in this room is nitrogen. Okay, about maybe 78%, something like that. About 18 to 19% is oxygen, and then everything else: carbon dioxide, water vapor, methane. Everything else would be a few percentage that are left. So most of the air is nitrogen. And then not only is there nitrogen, you have nitrogen oxides, nitrous oxide, nitrogen dioxide, dinitrogen oxide. They have all sorts of other. Now, in plants and animals, especially animals, plants too, when you see or think or hear of a protein, every protein has nitrogen. Every protein. Proteins are made up of amino acids, which are an amine group and a carboxyl group. Every amine group, the amine is NH3, NH2, NH4, something like that. Every one of them has nitrogen in it. So they're very essential for living, things. They're in some other things, but it's not nearly as predominant as oxygen and carbon and these others. Now, the funny thing is carbon doesn't show up on either one of these either, especially since that's the byproduct of your collisions and stuff. But again, most of the carbon is in carbon dioxide. Or the carbonates, like calcium carbonate and sodium carbonate, aluminum carbonate, magnesium carbonate. That's where carbons are in solid form, but they still don't make the top 8. They're in the others. In fact, I would think they'd be one of the top ones of the others.
Wouldn't coal be carbon?
Coal would be mostly carbon, exactly. But you see, percentage-wise, there's not that much. I mean, around our area, there's plenty of coal. Now, I say that. There is plenty of coal, but it's not really clean coal. It's got a lot of silicates in it. Silicon and oxygen, So, yeah, even then, the silicon and oxygen will way overpower the carbon. Okay, so yeah, you're right. It is up there. So I would think carbon has to be one of the top in the others. They just aren't in the top 8. Okay. All right.
There's more nickel than aluminum.
Yeah, in the whole planet. You're absolutely right. You see, aluminum is a very light metal, so it's near the surface, and nickel is a heavier metal, so it's further down into the core. Okay? But on the surface, aluminum is number 3. But it's number 4, 5, 6, 7. Okay. So it drops big time. Okay. Interesting breakdown. All right. Now, the name of the chapter is Rocks and Minerals. But the way the book is divided up is minerals and rocks, okay? So we're going to do minerals next, and then we'll do rocks, okay? So 17.2 is dealing with minerals, okay? Earth science definition of minerals. Now, there's several key elements here, so catch them as they come by. Number 1, naturally occurring. Okay, naturally occurring. Number 2, inorganic. Inorganic. Anyone know what that means? What's the difference in organic and inorganic? Okay. Organic means it came from living things. Okay? Like organic fertilizers. Okay? Manures and things like that. Or leaf mold. Okay? Or anything that came from living things. That's organic. Things that came out of the planet out there, that is inorganic. So to be a mineral, it needs to be inorganic, solid, not liquids or gases, an element or a compound with a crystalline structure. Okay? So several features here. Naturally occurring, inorganic, solid, with a crystalline structure. Okay? Now, Look at the converse of those. If it's not naturally occurring, it's synthetic. In other words, man-made. Okay? Now, I think we talked about this before, a little bit earlier. When I drive into work, coming south on 59, west on 20, through Malfunction Junction, about Arkadelphia Road and along in there, off to the right is a big, huge mound of some whitish-looking material. Now, that's just before you get to most of the iron stuff. And
What is that supposed to be?
what's that?
I've always noticed that. What is
Okay. I don't know for certain, but that's what I was going to guess at next. All of the coal burning and production of steel and all the other things that require lots and lots of heat and heating things up and melting out the things you need and letting the rest go. Sort of the residue from that is, I think, what they call slag. Is that the right word for it? It's like when you're doing the iron processing, you put in the ores, you heat it up and stuff, and the iron goes out. There's a skim of stuff on top that they rake off or somehow get off of there, and then it solidifies later. So all that kind of stuff, and then when you're burning coal or other things, the silicates and the other things that are parts of the coal, but they're not useful parts, they're not coal, they get melted and then recrystallized or re-solidified. That's synthetic. That would not be minerals. And my guess is what that mound is. That's a mound of slag. Now, I'm not certain it is, but I bet you that's what it is. The stuff, the residue from some of the other activities that have been in the area for decades and centuries. Okay, so I think that's what it is. Now, I don't know for sure, but that's my guess. Okay, so that would be synthetic because man made that. Okay, now originally it started as mineral, but we modified it. Okay, there is a lab over in at UAB, because I took a course from the physicist. No. Oh, he was my advisor when I took some courses over there, and he did the diamond lab. They made synthetic diamonds there. They took carbon and put it under great high temperatures and a lot of pressure and made very small, not very, but they're industrial diamonds. Those would be synthetic, man-made, not naturally occurring. Other diamonds are naturally occurring, they're diamonds. Okay. Those are minerals. Not directly produced by a living organism, that means inorganic. Okay? In other words, the process that produced them was not a living process, but a physical process. Okay? And it must have a regular repeating pattern. That's what a crystalline structure is. We'll talk about that next. One example of this is halite. Halite is a mineral that the primary ingredient in it is sodium chloride. Now, I'm not absolutely certain, but I bet you this is pretty much what, any of you make ice cream in the summertime? What you put on the ice so the ice, and what kind of salt do you call it?
Rock salt.
Rock salt. And if you notice, the residue from that has some blackish and brownish and other things. It's not salt I would want to put on my food. In fact, I don't think anyone puts it on their food, do they? Because it's probably a naturally occurring mineral salt that has silicates and other things in it that you wouldn't digest too well. Okay. What they do is the salt that we put in a salt shaker, they usually, I think they get that from seawater. I'm not sure, but I believe that's it. Whatever they do, they melt it and then recrystallize it and have pretty pure sodium chloride. Halite, though, is a mineral sodium chloride. So let's take a look at that sodium chloride mineral. Now this, yeah, they corrected it in your book, but on this slide they didn't, okay? It always bugged me when I saw this to realize they had one of these colored wrong. And so here's what we have. The green ones are sodium ions, and the blue ones are chloride ions. Now these are just for illustrative purposes. If they really drew these correctly, the sodium ions would be pretty small, the chloride ions are a lot bigger. And here's why. Does anyone know this? Okay, let's go back here. What makes an ion as opposed to an atom? An atom is always electrically neutral. Or a molecule is electrically neutral. Same number of protons as you have electrons. Got to be an atom or a molecule. To be an ion, you either have gained an electron or lost an electron. You never gain or lose protons. That's a nuclear reaction to make that happen. You gain or lose electrons. They're floating around in the outer shells, and it's easy to gain or lose those. So when they say sodium ion, that means it's a sodium atom that lost an electron. Now, why would a sodium atom lose an electron? Well, if you find sodium in the periodic table, there it is. Row 3, the first element, first column, Na, sodium. Natrium is where the original Latin name was. We changed it to sodium, so that's why it's Na. Now, let me explain a little bit about the periodic table for you. The structure, the electron structure in all atoms, they start with what we call the s electrons. And the s electrons can only have 2 of them. The first s electron, hydrogen, helium, that fills that shell completely. The next shell, number 2, has s's and p's. 2 s's and then 6 p's. That last one, neon, has a full shell. Helium's a full shell, neon's a full shell. The next one, 2 s's, 6 p's, argon's a full shell. Okay? Absolutely every place is occupied. Okay, now let's back up. Hydrogen only has 1 electron in a 2 electron shell. It loves to either gain or lose another electron because it wants a full shell or an empty shell, but one or the other. Okay, mostly it shares electrons and gets out of the electron. Lithium loses that. It has 1 electron floating around in the outer shell by itself, so it's real easy to lose. Okay, sodium, same way. It has a full shell down here with neon, and then 1 more electron's added. It's not in any shell, poor old thing all by itself. Nobody can play with, you know. So it's just out there floating around, real easy to lose. Well, that's what's happened. Now, where did it go? Well, let's go on across the shell here. Just before you get to argon. Okay, good, you got it. Just before you get to argon, which has a full shell, you come to chlorine. And chlorine has 7 electrons in the outer shell, and it wants to have 8. It wants so badly to have a full shell. So what does it do? It rips off 1 from the sodium. Because all the electrons are electrons. They don't care whether they came from a sodium molecule, an atom, a chloride ion, a carbon ion, a uranium ion. It doesn't care.
How do you get that from this here?
From the periodic table? Well, everything in the 7th column has missing just 1 electron to have a full shell. Everything in the 8th column has a full shell. Everything in the 1st column has just 1 electron past the full shell. So these tend to lose them and become positive ions. These tend to gain them and become negative ions. These don't combine with anything. Helium doesn't combine with anything. Neon does it. Argon does it. Krypton does it. Radon, xenon does it. not even radon. Radon, look at that. Atomic mass around 222. That's a big, heavy atom. You know what it is? It's gas. Because it doesn't combine with anything. Okay? Everything else within 3 rows of it are solids. Okay? It's a gas. Well, except for the other. All these are gases. Probably just float around by themselves. I don't think I've ever seen so much rain for so many days in a row. Wow. But I'm not complaining yet. So we start floating away or something. My wife said I was supposed to go home and grill the chicken unless it was raining. I think I get out of grilling chicken today unless it lets up in the next few hours.
Is out at my house.
What's that? The power is out?
And it's fed from this area that was hit. So I may be without power for a couple of days.
You're kidding me.
Yeah.
Oh, man.
I'm looking, I need to leave. I'm gonna gas my generator and all of that stuff.
Oh, okay.
I had my gas can out about to get gas.
And
It's still sitting there on the back of the pickup truck. Someone told me to get gas.
yeah. And you just
Gotta find some gas.
well,
could have been worse.
huh?
Could have been worse.
Yeah. Do they really think it's going to be that long before they get it back?
Yeah. They haven't even started cleaning up yet.
Oh, you mean, okay, it's because of
Yeah.
tornado damage or something? Wow, are you that close?
My power is fed from that side.
Oh, that side.
Yeah.
Yeah.
Unless Alabama Power can reroute it some kind of way.
Oh, it's gonna be. Everybody.
Yeah.
This is a lot of power outage in Jefferson.
Is the active weather still happening pretty much, or is it just rain now?
It's rain.
Okay. Well, that will hamper them getting it cleaned up and repaired.
Yeah.
Because you don't want to mess around with electricity if it rains too much. But at least maybe no new damage is happening. Yeah. All right. So that's okay. That's why I said sodium is a small ion, because it's lost an electron. So now it has, if you go to the periodic table, it has 11 protons, but only 10 electrons. Well, every sodium always has 11 protons. I mean, that's what makes it sodium. But there's only 10 electrons around, because protons tend to attract electrons. That brings the shells in to make them smaller. Whereas chlorine, if you go to look at it, it has 17 protons, but 18 electrons. So because it has excess electrons, they try to get as far away from each other as they can. So the chloride ion actually gets a little bigger. So that's why I said these aren't to size, they just made them colors. So this will be a little one, a big one, a little big one, a little bit. Now notice here in your chart, sodiums are only, okay, now, okay. So chlorine has ripped off an electron from sodium. You would think they go the merry way, right? No, they don't. What is sodium now? A plus charge. What is chlorine now? A minus charge. Guess what one of the strongest forces is? Electrostatic attraction. So now they're drawn together, even though this one lost an electron, that gained an electron, now they're pulled together because of the electrical charges. And they hold together, and this is really a good representation. It's called a cubic crystal, okay? And that cubic crystal has sodium, chlorine, sodium, chlorine, sodium, chlorine. Every other one is the opposite. Sodium, chlorine, sodium, chlorine, okay, sodium, chlorine, sodium, chlorine, sodium, chlorine. The bonds here are always adjacent to the other. Can anyone see something miscolored on this chart? That one right back there. What should that be? Green, because you never have sodium bonded to sodium. They would be repelled from each other because they're both positive. This sodium could be bound to that one. You notice this one's not bound to that one, this one's not that. They're only bound to chlorides. that should be a chloride ion. They say chlorine ion, it really should be chloride ion, sodium ion. Okay? And that unit, except that should be a green there, that unit is repeated all over the place here. That's what makes it a crystal structure. Crystalline structure is repeated organization, very rigid, regular organization, repeating pattern that repeats itself throughout the crystal. So anything that's in crystal form, that's what it's got. Minerals are always crystalline structure. We'll find some things that are surprisingly not minerals later. Okay? So let's look at some of these crystal structures. Before we go any further, though, they have mistakes and misunderstandings. Okay? Healing crystals, that was a big topic, what, 10, 15 years ago, maybe still. Practitioners of crystal healing have long held that certain crystals have physical and mental healing. I don't know. This guy doesn't seem to believe it. I'm pretty doubtful myself. But I don't know. We don't know everything. Figure 17.4, they don't show in the slides, I don't think. So this is a structural unit of table salt, which is sodium chloride. And you can almost look at those and tell they're little bitty cubes. If you took a salt, shake it out of your shaker, put it under a magnifying glass or a microscope, you'll see they're almost all perfect little cubes because of that cubic structure we saw before. Okay? So let's take a look at some of these crystal structures. Now, before you panic, you don't need to memorize these things. You don't need to learn them. This is just to give you an idea of the different kinds of crystals they can have. Okay. The first kind here, Got to read this. Crystals can be made up of one or more kinds of elements. If all the crystal is made up of the same element, then that's an elemental crystal. If it's made up of different elements, then it's a compound that's a crystal. Diamond is only carbon. Now say only carbon. If you ever see, and you'll see them some days, they'll have things like chocolate diamonds or pink diamonds or something else. Those have slight impurities in them. They're still diamonds, but they have something else that changes the appearance and the color. Okay? So, it's not only carbon, but largely carbon. A pure diamond is clear, and that's only carbon. Okay? Whereas a quartz, which has a crystal structure also, is silicon and oxygen, and usually in what we call a tetrahedral form. One silicon in the middle and four oxygens around it, and we'll talk about that just a bit later. Okay? So that would be a compound that's a crystal. It's an element that's a crystal. Elements are all one atom, types of one atom. All the same types of atom. Compounds have two or more different kinds of atoms. Okay, now the classification is based on what they call the surface symmetry, what you see. 6 major systems, okay? And then there's sub-pieces of some of these systems. The first of these is isometric, and again, don't try to memorize these. I'm not going to ever ask you, which is this, you're going to define this. This is just to give you an idea of what's out there. Now, just to give you another idea, does anyone know what the prefix iso means? How about the root metric?
Isolated.
Okay. You're really close to it. Okay. Metramine is to measure. And iso, you said isolated.
Close.
Okay. No, not quite that. Iso means same.
Same.
Okay. So isolated would be apart from anything else. Okay? Isolated. Now, do any of you know what a topographic map is? Say again? A topographic map is one that shows elevations on it. Okay? And they're usually lines that equal elevations. those are called isoclines because they all have the same measure of elevation. So a pond or a gully, you would say those lines getting closer. A mountain, you'd see the lines going around. Until you know the numbers on them, you don't know if that's a depression or a mountain, but those are the isoclines. The weather map. If you've seen the weather map they show, they'll have these things, and usually this type of thing here is either going to be a high pressure area or a low pressure area, because that is an isobar. Same barometric pressure around here, getting higher in here or getting lower in here. Lower in here we have weather like this. Higher usually is pretty clear and pretty hot. Yeah, whatever. Okay. In the wintertime, cold, you know. So ISO means the same. Same measure is what that's saying. Isometric. Okay? You have other things like a triangle. Isosceles triangle. Two of the sides are the same. Now, here is one isometric crystal, a cube. All three of those dimensions, how many is that? 8 of those length nodes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All 12 of those sides have the same length. That's what makes a cube. Okay? Square is a two-dimensional thing that all 4 sides are the same. Give another dimension there, and all 12 lengths are the same. Isometric. Cube is that. Sodium chloride is a cubic isometric crystal structure. Here's another one, okay? An octahedron. Octo means 8. Hedron means basically sides. You have 3 triangles here, 1, 2, 3, 4, 5, 6, 7, 8. And every one of those has a equilateral triangle. So all the sides are the same. This side, that side, that side, that side, all are the same. Okay? Another isometric crystal. This is a tetrahedron. 4 sides. 1, 2, 3, and 4. Okay? And all 3, and these again, equilateral triangles are all 3 lengths are the same on every one of those sides. Silica, I said, was tetrahedral structure. Silicon in the middle and 4 oxygens around. Okay, at the points of those vertices of those triangles. And this is a weird one. A dodecahedron. Okay. Now, I think I counted this up one time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think there's 12 in there. I think that's what dodeca means, is 2 and 10. Dodecahedron. A 12-sided figure, and all the lengths are equal. Okay? And I get dizzy looking at that, trying to picture where those things are. But all these lengths are the same. Think a soccer ball, kind of. It's not quite the same, but it's pretty close. All those segments of a soccer ball are just about the same length, I think. Okay? So those are 4 samples of isometric crystals. Let's go to another kind, the hexagonal crystals. Now, hexagon is 6-sided figure. Okay, I don't know where the hex comes from. The 6-sided figure, and you see 1, 2, 3, 4, 5, 6. 6 equal, and not always equal, but I think these are usually equal. Now, notice these sides aren't equal, but the hexagons are equal. It's a little dark for this time of day, isn't it? What does the weather show us? Is it that real dark orange part? Is that on top of us now? Okay, that's why it's so dark. Got a lot of clouds up there. Maybe by the end of the class it'll be cleared up. Can you see the back side of it yet, or is the whole screen covered? I still think we're safest here. I don't think on the road is very safe yet. Okay. So this is six-sided figure, but not everything is equal. The hexagonal structures are. And we'll see some pictures in the text of some things that are hexagonal. Okay? Now this is a rhombohedron. Okay? And if you, it almost looks like a cube that's something else. Well, the difference between a cube and a rhombohedron, the cube, all the angles are equal as well as all the sides. In a rhombohedron, the angles may not be. So think of a cube that you sat on, okay, and it sort of twisted a little bit, okay. Now some of the angles are wide and some are narrow, okay. That's still equal-sided, but it's not equal angles. Now when we did built our house over on the farm in Georgia, we built in the middle of, we built in the cow pasture, okay? And we wanted just to fence out the cows just for the part where the house was. We didn't want to fence. I didn't want too much grass to mow, so I didn't want to fence it too much, but I wanted plenty of room to drive, and get everything done we needed to do. And we didn't need everywhere from where the house stands to the road, so we just did the driveway, fenced that in too. There were 4 big old pine trees. I mean, been there forever, longer than we've owned the farm. Okay? And 3 of them were here, and 1 of them was here on that side of the driveway. And the cows love in the summertime to be under those pine trees, so they're pretty cool. Okay? So I wanted the cows to be able to go back and forth pretty freely, but our house and the driveway were in the way. So rather than, and then we also needed some way, so my wife doesn't like to open gates and stuff, she wants to just drive through. So what I said, my brothers think I'm a little nuts. Rather than putting one gate there at the fence, you had to fence the cows in, and then have to open and close the gate whenever we were here. What we did, I put a gate here and a gate here, and these were swinging gates that did this way, these went that way. So that when we're there, we open them up this way so we can go in and out, and the cows are stuck here. But when we're not there, which is most of the time, they close this way, and the cows can go back and forth between the pine trees without any problems. Cows don't like it when we're there because they have to get around the house to get to the other side, but that's okay. They can live with it. We're not there that frequently. And my brother said, "Well, you've got a square here." I said, "No, it's not. It's a rhombus. So he said, "The square gate." I said, "No, it's a rhombus gate because the angles weren't equal." It drove him nuts. Okay. I said, "No, this is a rhombus gate." So from now on, he's been calling it a rhombus gate. I'm not sure he remembers what a rhombus is, but it's a rhombus gate. The sides are supposedly equal, but the angles are not. Okay, so those are 2 types of hexagonal structures. Okay? And for the life of me, I can't figure out where they get the hexagon out of that. Hexagon is supposed to have 6 sides. Oh yeah, it does. Think of it. Top and bottom, side, front and back. Yeah, that's 6 sides. So it is a hexagonal shape. Well, a cube is a hexagonal shape, but it's isometric. A rhombohedron is not isometric. Okay. Here's a prism. Both of these are prisms. This is the tetragonal shape. Now this is a tetrahedron, 4-sided. But a tetragonal shape would be 4 sides, but it has another dimension this way. So these 4 triangles are tetrahedra, not quite like this, but 4-sided figure here and 1 here, and then 4 sides here. And that makes a prism. And so a long side like this, that's what makes a prism. There's a prism. Okay? Then we have orthorhombic. And again, you don't have to remember that. Orthorhombic. Rhombic means the angles aren't equal necessarily. These may be wider and these narrower. Those are wider. So it's a rhombus, not a square or a cube. But ortho, they're not as equal as sides. And again, this is a prism structure. Monoclinic, I can't figure out where that name comes from. This is a prism, but it is a regular crystal structure. Pointed here and here, there and there, parallel here and here, and pointed here and here. Not much, but a little bit here. This is another type of monoclinic. And this is triclinic prism. I'll look at that and say, what is tri about that? Tri meaning three. I have no clue where they get that name, but that's the element. But these are all different types of crystal structures you can have. Okay. Now, I was trying to picture for myself what a diamond would be. A diamond would definitely have something of a structure, crystal structure like this, that you have those really incredible facets and angles to it. Okay. And we'll see some crystals, minerals, when we do the next lab. I've got some that you can look at as well as you'll be looking them up. Here's pictures of the crystals. The one in our book shows the top of a salt shaker. This is actually a micrograph taken from a microscope. Now see, every one of these crystals are little cubes. Now the thing is, they're sort of rounded on the edges. They're not perfect cubes because they've been weathered somehow, but every one of them is a little cube. Okay? This one looks like it's fractured a little bit. On the other hand, these are quartz crystals. Quartz, remember the salt crystals, sodium chloride, sodium chloride, sodium chloride. Okay? The quartz crystal are silicon dioxide, silicon oxides. And these are, you can't quite see here, but these are those, I think, tetrahedral structures. I think. So many times quartz will have that characteristic on the end. But you see, there's different crystals put together different ways, but there's another one. Look at that, and look at the one right there, that tetrahedral. Don't these points here and those prismatic structure there look a lot like what you see here? There's the point, and there's the sides. Here's the point, and there's the sides. Here's the point, and there's the sides. I can imagine that on a few guys. And right there's some smaller ones here, and there's the sides. Okay. I don't know for sure that's what quartz is, but it looks like that to me. Okay? Now, someone remind me what the two top elements on the crust of the earth are. Say again? Silicon and oxygen, is that what you said? Absolutely right. Actually, oxygen first and silicon. Is that what you said? Okay. Yeah, of course you did. Okay. So, and guess what silicates are? Silicon, oxygen. Okay? So it would sort of reason that most of our surface minerals would be silicates. Okay? What are silicates? They contain mostly silicon and oxygen. Silicates. That's what the prefix 8 means. Silicates make up 92% of the Earth's crust. I would say that's most of it, wouldn't you? Okay, 92% of the Earth's crust is made up of some type of silicates. Based on the silicon-oxygen tetrahedral unit. Silicon in the middle and 4 oxygens around it. Now, some of those oxygens are shared with other silicons, but that's the basic unit. 4 major arrangements. And I think these next slides will try to show these. I don't think they do a great job, but they do okay. Okay, here, this is the one here. The silicon-oxygen tetrahedral unit. There's a tetrahedron. There's a triangle, 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 and then the backside of the triangle. Okay, what's that triangle made up of? Silicon in the middle. These 3 oxygens make this triangle. These 3 make that triangle. Those 3 make the back triangle. And these 3 make the base triangle. Okay? Not a good 3-dimensional picture, but you get the idea. Silicon's in the middle. Why silicon in the middle? Silicon's a +4 ion. So you talk about small. Those protons in the middle have really drawn those electrons. You've got 4 fewer electrons than you do protons. Really made that small, where the oxygens have 2 extra electrons, so they're big fat things around here. So these really look like the oxygens look like sumo wrestlers, big fat places fall around, and the silicon's stuck in the middle, a little bitty thing wedged in between that. And actually, these figures aren't too bad. Okay? The little green in the middle is your silicon, and the big blobs here are your oxygens, the reddish blobs here. And they've drawn in, connected the centers, and that made the tetrahedral structures, whereas really they're bulged tetrahedrons. Okay? Boy, this has been going on all day. What does it seem like?
You're not saying anything, but I'm looking at
You're not saying anything. As soon as you hear something, let me know. Huh?
West Central Shelby and Southern Central Jefferson. It's around 18 on Valley.
Oh, yeah, it just popped up.
Places impacted Hoover, Alabaster, Bessemer, Pelham, Galena.
Bessemer, you said?
It's coming right to this.
Okay, and what is it? Thunderstorm? Tornadic? Or what?
Circulation.
Yeah. Think we ought to go down?
Let's take this test group.
Well, we can take the test down there and take it down there.
Let's take our stuff down there and take the test.
Huh?
Can we take our stuff down there and take the test?
Yeah, that's what I'm saying. Let's do that. Okay. I'm going to take a minute to get shut down here. Go to that classroom unless somebody else is in there. Even if someone else is, stay near the door because that's where I'm coming. Because I want to shut down things up here too. All right. Remember, this is the slide we're on when we start next time. Okay, and it'll take me just a couple minutes to get down there. So y'all hang tight, I'll be there. Oops, that's not on. I forgot to mark y'all here. I'll get you when I get down there.